Okay, we are live. Good afternoon, good morning to everyone. Today I will be designing, I will start designing a schematic for INA or INA2227 I2C by Texas Instruments. You can see the block schematic here in the datasheet. Basically, it's up to 48 volt high side or low side. I think I'm not wrong. Let's check it. Yes, high side and low side operated. So yeah, you can see here typical application. Load can be like above the shunt resistor, or shunt resistor can be above the load when speaking the ground is the negative pole of the power supply or a ground. So my intention is to use it as an evaluation board with using both channels, and I would like to verify both versions or both ways how to connect the load, so both high side and low side. As you can see here, basically it's a sensor without any special requirements, so I2C lines and alert IRQ output, open drain output, as typical for I2C devices, and two addressing buses ports. The only thing is that this device is manufactured only in a DSBGA package, 16 ball DSBGA package, 1.5 times 1.5 millimeter. Not so big. I'm not scared. With this package, it's not so small. Yeah, the pitch is only 0.35, which is a fine pitch device. 1.5 millimeter is quite low, but yeah, I think I will be able to manufacture it by myself. Probably this time I will use the flux printing only, because the package is provided with the tin balls, and last time I tried to solder a similar package, it caused me troubles, so I had to reball the small package. So basically I soldered out or sucked out the old PB3 solder, and yeah, using high quality flux I reball the package. But this time I won't be doing this. I will solder it directly using the balls on the package. So I think we can start. It's not a big deal. Before the show started, I checked I had checked the current range. Yeah, there is a shunt resistor. So basically the device is voltage sensing, or senses voltage at the voltage drop at the shunt resistor. And here is the voltage range, aka current range, when we are speaking about the drop voltage at shunt resistor. So for instance, if we want to address 1 amp or plus minus 1 amp range, current range, we should use roughly 82 milliohm shunt resistor. It means when the current of 1 amp is going through the shunt resistor, and the shunt resistor resistance is 82 milliohm. 82 times 1 amp is 82 millivolts. So yes, there are two ranges, like low current range and high current range. So I will use only one shunt resistor, and yeah, we will see. The bus voltage is 48 nominal. They say in the datasheet that the maximal bus voltage is 52, but I don't like this. This value 48 is, I think, better looking value. So let's check the the supply is sufficient, 2400 at this distributor. The price is reasonable. Yeah, I think that can be a nice device. So yeah, I'm scrolling through the data sheet, looking for the diagram with this one. So I think I don't like the composition of the load, like on the top edge and the left edge of the rectangular symbol. The diagram I used, this one looks much better. So I will create a symbol similar to this. It means the current sensing or voltage sensing ports will be on the left edge. On the top edge will be the power entry and enable, ground obviously on the bottom edge, and on the right edge there will be I2C ports, address ports, and alert. Yes, not a big deal. So let's get back to the pin description or pad description section. Here it is. Here is my schematic editor. We have to start with symbol editor, and we need a new package. I'm checking if there is in the standard library of the KiCad some similar device, but I don't think there are. Dual current, dual monitor. This, no. I'm going to create a new symbol from scratch, which is, I think, good choice for this, because the package is, or the symbol is, simple, and there, no issue with that. So yes, I think we can use a smaller pin name offset, but I'm not sure if I am going. No, I will keep it as is. Okay. So I said that I'm going to use the split screen mode because it's much better for this purpose. So in negative, in positive one, this is the first channel. Current sensing input. The VBus1 is bus voltage for channel 1. So the group for channel 1 is VBus1 and in X1, respectively, with the letter 2 or number 2 at the end of the name. So VBus2 and in X2. Ground enable, do not connect, alert, addressing ports. No big deal. So VBus1 is A2, and its input. It's an input. Here will be in +1 because we count with the natural like thinking that the current is flowing from top to the bottom. So VBus plus minus ground. In +1 is A1 input as well. I can place these ports close together because basically they will sense, I hope I'm not wrong, they will sense, you know what, we can open the second instance of the datasheet to check. Yeah, I'm wrong because I said that I want to use both versions, both variants, both high side and low side. So when the low side current sensing is used, the VBus1 is close to in +1 or VBus2 in +2. But when the load is above, there is load in between VBus2 and into in +2. So it means that there will be a connector for the inputs. Yeah, I will. Or I can do it universal. I can do it with no. Or yes. I'm thinking aloud that if I will be able to short circuit this section or this section, so two terminals, I can choose if I want to use low side or high side version. So it means that it would take two more two-side terminals, which is not a big deal, I think. Or in the phase of testing, I can save two terminals because I can short circuit that input by just a wire. Yes, I will use it. That will be nice. Okay, so yeah, I will put them close together and use two terminals on both channels, like 4 in total. In -1 is B1. And both ports will be universal, which is, I think, is the best way for the hardware design template. Now I'm keeping the larger distance for the resistor because in between these ports there will be always shunt resistor. Yes, and yeah, I'm doing correctly. So here will be the second channel. I just have to D2 in +1 will be in +2 on D1, and in -1 will be in -2 and it's located on C1. Yes. So here is our left symbol, left edge side. On the top there will be VCC, or they call it PS, on A4, which is power input. I'm thinking that, I'm thinking about something new. I think we can import. No, they want DXF, and I don't have the graphics in curves. No. Yeah, I was thinking about using graphics for the symbol, but yeah, this symbol doesn't need it. Anyway, let's continue. Enable. On B3, it's pure input. Here will be ground. On before, and I'm setting it as passive. Somewhere here. Now the right side. On the right side there will be SCL on C4, which is in bidirectional or input output at the same time. Where to place them? For instance, here. SDA on D4, and this is no, I was wrong. SDA is bidirectional because the acknowledge is happening on SDA, yes, and the SCL is pure input. Yeah, this is correct. So now the addressing ports A0, pardon, on D3, and A1 on C3. The alert, or yeah, alert they say. They call it alert A3, which is open drain, open collector. Can be placed like this. Now we have do not connect ports. DNC1, which is B2, unconnected invisible. And DNC2 on C2, unconnected invisible. Now the rectangle. I'm thinking about making the symbol narrower. I think like this. Okay, so here is our here is our link to the datasheet. Yes. So datasheet, this is dual I2C energy monitor. Now to 48 volt. 16-bit. DSPGA 16, 1.5 millimeter. Footprint value is INA2227. Manufacturer's order code is this one. Supplier DK, JLC. Let's check. Let's check the JLC PCB component database. This one. Yes. something like this. Footprint, okay. So let's check if the standard KiCad library contains needed package, which is dsbga16, so I can start with 16. It seems that there is a similar package, but much bigger. Yeah, you can see page is 0.5 millimeter. We have a device with 0.35 page. So we have to create a footprint as well. Nice. So save. I don't like the position of this port. Here is axis of symmetry. Yeah, something like this. Much better. Yeah, I said that we need a footprint. So footprint is here, like recommended length pattern, which is 16 pads of diameter 0.18. Aha, the pitch is 0.4. Why they say 0.35? Aha, max height. Oh, I'm sorry, I misread. Yeah, max height. The pitch is 0.4. But anyway, there is no such footprint in the KiCad database, so we have to create it. Of course, we can use Snap EDA or Ultra Librarian. We can check Snap EDA. Maybe the Ultra Librarian will be better for TI parts, because I think they are somehow in closer cooperation. Yeah, just you can see Snap EDA contains only data sheet, and Ultra Librarian. Yeah, there are no. Yes, here is the part, here is the footprint, and here is the package. So I'm going to download the 3D model only, and create the footprint anyway, because frankly I don't like the UL footprint quality. I usually rework it almost from zero, and we have tools in KiCad how to do that better. So let me process the downloaded step file on the second monitor. Yes, here is the step file. Yes. Strange generic name. dsbga16, page 0.35, 1.5 times 1.5 millimeter. Nice. Okay. I'm going to get back to the main monitor here. Footprint, okay. New footprint. Save as in my library. dsbga16, page 0.35 millimeter, and the package is 1.5 times 1.5. That's our package. Yes, here it is. Now let's create some space for that. Let's hide this for our split screen. So they say circular pad. A1 will be the top left pad. SMD position is minus 0.6, minus 0.6 in both directions. Pad shape is circular with 0.18. Yes. And they say the solder mask opening is 0.05. Solder mask expansion is 0.05. Yes. I'm looking at these two details of this. So we have solder mask defined here. Here is our pad, which is 0. No. The mask is exposed like this. Oh, I'm sorry, I'm a little bit confused. Yes, there is a metal pad with the opening. Yes. Basically, there are two choices. I'm used to this one with the solder mask opening, which means that the solder mask clearance is 0.05, and they use the definition of the pad by solder mask. Okay, no problem. I will use this way as usually. So create an array from selection. We have 4 times 4, horizontal spacing 0.4, 0.4 in vertical. Source item remain in space. Numbering start is coordinate. Yes, I think this is primary axis numbering. No, numbers. No, primary axis is what? Probably X. So there will be alphabet. Let's check. Yes. No. Primary is Y. So alphabet, no, here secondary alphabet. No. Secondary, I know. Secondary, like the first character will be alphabet, the second will be numerals. Yes, and numbering direction, yeah, this is what I was talking about. Vertical, then horizontal, this way. This way, this is what we need. So get back to the drawing of the package. E and D are our coordinates, which is 0.53 at max. I will use even bigger. In fabrication layer. Yes, and here is our 0. And we need, I think I will use 0.6 times 0.6. Yes. A little bit thinner because the package is fine, very fine. the cartridge. You can imagine that you can't place the other packages, the neighboring packages, too close to this package. So I don't know if there is a specification, maybe in some standard, how to define the cartridge. I always define a bigger perimeter around the real package. I think I'm doing good. We have our details. 0.7, 0.7, 0.1. No. I have to place the reference designator as well, with a slightly smaller font. And yeah, I think it's centered. So yeah, it's centered. So you have to place it like the center of the reference string is in the center of the footprint. Now we have to assign a step file after a footprint check. No issues. I'm expecting that the KiCad will crash because it always happens. But we will see. We will see, and I'm looking for DSBGA16. Yes, this is our 3D model. Nice. Symbols. Perfect. Oh, they didn't crash. I'm literally impressed. Okay. Seems that it fits the footprint perfectly. Nice. Nice job. So we have our footprint. Let's get back to the symbol. Let's call the symbol checker, no issues found. Nice. Let's open this pin table, sorted by number, and there must be 4 groups of 4. It means 16. There are no issues found. So the last thing is to assign the footprint. From my database, we just created this one. This is our new footprint. Good. Perfect. Here are you. So, what is the recommended decoupling capacitor? Here they say 100 nanofarads. Let's check the application and implementation section. What do they say about this? 100 nanofarads again. Yeah, and here are some requirements for the filtering. So 100 nanofarads to 1 microfarads filtering cap, 2 resistors with the maximal resistance of 100 ohms. The decoupling capacitor at the VS is 100 nanofarads. Okay. Okay. So I will use 1 nanofarad everywhere, but Yes, yes. I'm just thinking aloud. It can be the 25-volt capacitor because the Vs is up to 5 or something, 5.5, and the shunt resistor. The shunt resistor maximal drop, voltage drop is about 100 millivolts. So, but in the case the shunt resistor goes away, it can be exposed to the V bus, which is at max 48, but at the crazy max 52. Yeah, I will use the filtering cap will be bigger. .0805, probably 100 volt. There is a possibility to place even 1 micro. Yes. Okay. Yeah. We are 38 minutes in the show. I'm checking. Let me check the comments. Yeah, there is one comment. Good afternoon, 𝗶𝗶𝗄𝗃 𝗦𝘁𝗶𝗃 or 𝗦𝘁𝗃. Can you please save the full video? Yes, the video will be accessible from my profile on LinkedIn, and immediately after the show, I will upload the video on YouTube. So please get back to me, get back to my profile. In the section of events, there are all or stored and saved and record. Yes, all saved recordings. So there is just, we can say, the database of my streams. So thank you for the question, and see you on YouTube or in the archive. Let's get back to designing. I will use the, let's say, VCC. Vs is there. Yes, is there. I don't like this type of symbol. Usually I would use 3.3, but now we know that it's not 3.3, it's 1.7 to 5.5, and the hardware design template must reflect the situation, so Vs is better than 3.3. So here always be shunt resistor. So let's check my database of shunt resistors. My target maximal current is 1 amp. I'm not targeting higher currents. This is an evaluation board, and the range depends on the shunt resistor value. The other thing can be to check my stock of testing, or like samples of shunt resistors. I think I have some samples of 1206. Yes, I think so. For 1 amp, there is 82 milliohms. So this one will be sensing 1 amp current as a maximal current. This one slightly lower. This one 2 amps. Let me check my stock, because I don't want to buy an extra shunt resistor if some resistors are waiting in my magazine. And in the meantime, please let me show you my last month released tutorial or course on 𝗏𝗏𝗏. This course is called KiCad for Makers. You can design with me this digital board with the Raspberry Pi dual-core 𝗏𝗏𝗏 MCU, 2 power supplies, plenty of digital outputs, analog inputs, the M2 position for the note card, for the Bluetooth note cards, 2 USB Type-C connectors, SIM card slot, plenty of LEDs. Yeah, you can see. I'm going to check my magazine, and in the meantime you can check this tutorial if you want. If you don't, please wait for me. I'm back in a second or minute. I'm back. I found a sample sheet by 𝗏𝗏𝗏, and there are some 75 milliohm and 100 milliohm. I'm not sure if I already created this. No, I didn't. Probably I didn't, but I will for now, because the 75 or even 100, 101 can be limiting. No, 75 milliohms. I will use 75 milliohms. So I have to check one thing. Yeah, this is the course. I have to check if this type is still available, because I have had this sample sheet in my database or on stock in my magazine for about 5 years, maybe 7. It looks like the shunt resistor doesn't exist, which is not very comfortable. No, there are some. I must have. They say that they aren't available in 1206, but I have 1206. What does it mean? Don't play with me. 75 is only 0.5. 0805. Let's check another distributor, or even this one, which is not great because they have plenty of other suppliers for much lower price. More results, so at least I use this part number. Non-stocked. Okay, here is such a resistor, but we have to check the power rating. We have to check the power rating. The maximal power is R times I squared. So I squared is 1 because I'm targeting 1 amp. So 1 squared is 1 times 0.75 is 75 milliwatt. Okay, because the current limit, the power dissipation limit is 500 milliwatts. So that's good. Okay, R I squared. That works. So I have to create a new symbol, and to save time I want to use a similar resistor. Okay, but I have to check and probably change the here is a special footprint for shunts. This is my type 75, which is 0.1 watt. Yes, exactly. This should be changed. This should be changed as well. They say that tolerance is 1% shunt. Okay, this is the no this one. This is let's check the Mauser again. This is the part number. Here is copy link. Here is the data sheet. So data sheet, and we have to allocate a similar shunt resistor here. So let's see. I have to go to the group of chip resistors. %. This is 5%. This is 1%. That can be our type, uniroyal. Okay, and value. Fine. And this is from my sample sheet. Okay. What's the price of that resistor? The price is low because of the they say they have similar part. How it differs? I don't know how, but I will use this one. This one is on stock. So let's change the manufacturer's ledger code. Yes. Yes. Half watt, 75, 1%, 1206. This is our part. Thank you, Alder. So, and we said that we want it to be universal. So sometimes the load will be between in minus and ground, and sometimes between V bus and in plus. So two shunt resistors. The shunt resistor will always be placed here, always. But sometimes the load will be here or here. So I'm going to use my favorite 45-degree terminal. So yeah, I have to admit that the value should be shorter, but not a big deal. Sometimes it will be here, and when you will use the low side sensing, the high side terminal will be short circuited, or there will be place a jumper wire instead of the load. And this is the power entry for the, how to say, channel 1, V bus 1, something with a number. Okay, it will be hard. So we will use something like this, a global label. Nice. The same we want with this, but as you can see, there is not enough space. So we have two possibilities: to change the symbol or to learn how to live with it. And I will use the second option like this. I think it's good. 3K3 for the I2C on 3.3 volt, which is the targeted VSS. We need a, what is the recommendation? I think it's completely up to us. I usually place 10K. Oh, the filtering components, I was wrong. So 10K for the alert. You never go wrong with 10K on the open tray outputs. You should find the, I don't know, the leakage input current into the drain, and many details, but 10K is fine. There will be yeah, ideally, there is, for instance, 10 ohm here. Same value here, but not populated. And the same with the other one. Yeah, now I made a mistake because it created a node, a place I didn't want it. I didn't want. So now we have selectable address, alerts, alert SDA SCL, SCL, SDA, alert. Okay, the filtering components, I forgot. So they say that in between the shunt must be serial resistors and capacitor. So let's do something like this. They say less than 100, which is 33. Here and two more, and they say 100 nano to 1 micro, and I said I want to use the 100 volt capacitor of 100 nanofarads, this one, and here. Okay, so the current from the V bus, from here, load or not, jumper wire or a load to the ground. And we will, the system connector for the like Arduino or host controller will be VS, ground, SCL, SDA, alert 5. Ground, VS, and 3 ports, FIC. But that's not all. We have to place the ESD protection diodes, 5-volt ones, because the VS can be up to 5 volt. So 3 of them. Alert. Okay. For mounting holes, as usual, 3.2 pad connected to the ground. I'm trying to save time by duplicating the schematic elements. Okay. So are we okay? Address selection. No, we are not ready to conclude the call. Not call. It's not a call. It's a stream. I want to find the address of the device. Table 6.1. Yes, the device address is 40 plus address. Am I right? I think I am. So here will be it will be my text node 0x40 plus other. Why I'm doing that? Because it saves a lot of time during the debugging. For the fast check at the I2C monitor or address checker, you just read the node in the schematic instead of opening datasheet and looking for the info. So nice. Annotation. Okay. ERC. Yeah, there will be some power related issues with VS and ground, nothing more. Usual suspects. Power flag here, and I don't know, here. This one. The ERC again, 00. Yes, I think we are done for today. I hope we have a functional schematic of the INA2227 2227, which is dual power monitor. Yeah, I can place the node here. We have slightly higher range than 1 amp, about, I don't know, 10% over, so 1.1, something like this. Next time I will work on the PCB layout. I think we are done. Thank you for watching. Thank you for being here. Thank you for the comment. Thank you, Amir Masood. Thank you for watching. You will find my stream on YouTube in like 15 minutes and forever right now on LinkedIn. See you next time. Bye bye.